다음은 경희대학교 박우진 교원께서 3미러 시스템 광학장치의 이 광기계 설계와 진동 해석에 대한 연구를 발표해 주시겠습니다.
Hi, I'm from Kyung University and I'm Woojin Park. I will have talk in English, but if you speak Korean, ask me question in Korean, I will be really happy with that. So I will talk about the optomechanical design and vibration analysis for LF TMS. So LF TMS is off-axis 3 mirror system. So there is 3 off-axis mirrors with the internal speaker diameter of 150 and focal ratio of 3.3. And this is a very wide field of view telescope with a 5.5 times 4.1. So this optical design is quite unique. So let me explain with one example. So for instance, if there is 1 meter Cassegrain system with the on-axis system, and we have an identical point source image at the image center, and there is a coma aberration on the other field. This is normal aberration. But if we design to move on to the off-axis system, common off-axis system, there is exactly same optical performance at the center, but there is additional aberration on the other field, which is linear astigmatism. So actually, this astigmatism degrades image quality significantly, even worse for the wide field of view system. So, but if we design the off-axis system with the confocal system, we do have exactly the same optical performance with those of the on-axis system by eliminating linear astigmatism. So with this optical design, I designed the aluminum mirror. So as this material is aluminum, so we can just mount this mirror to the optomechanical structure by using the screws. So we put the screw, and there is shim structure between mirror and optomechanical structure. And also there is L bracket on the side of the mirror. So by changing this thickness of this L bracket and shim, we can actually adjust the mirror position for the alignment. So, and there is something thermal expansion slot on the side of the mounting position. This slot actually suppresses the assembly stress, also the thermal stress. So this is one of the examples, the simulation result. So I put this, the assembly torque for these 3 points. And there is, this color scale shows the displacement and stress. And this red part actually shows that there is many stress by assembly torque, and actually this part displaced by the torque. But if you see the mirror surface, this stress doesn't really move on to the mirror surface, so we can protect the mirror surface from the stress. So the results show that all M123 mirror has surface RMS error by assembly torque is around 53 nanometer to 120 nanometer. So with this design, we fabricate the aluminum mirror with the diamond turning machine process and nickel plating, and we did the MRF polishing to reduce the surface roughness. So these 3 figures shows that the surface figure error, and these 3 shows the surface roughness. So the surface RMS errors are 2.51 nanometer to 4.81, which is quite large than normal surface of the normal optical surface. But the surface roughness is around 2.3 nanometer to 4.99 nanometer, which is quite relevant values. And we also designed the optomechanical structures. The optomechanical structure has 4 big components, and this yellow thing actually holds the M1 and M3, and this gray one holds the M2, and this blue one actually suppress the straight line, so it's something like backboard. So, and we found that the many of straight line actually reflected by this M2 mounting surface. So that's why we put this group structure to suppress the straight line. and all the mechanical structures are designed by light structure because this LFTMS targeting on the payload system for satellite. So this is the pictures after we fabricated, and this small picture shows that the accurately assembly process of the mirror. So we use this precision shaft to accurately positioning of the mirrors. And this shows the assembled LFTMS. And as this system actually targeting on the payload for the satellite system, so we need to have analysis for the vibration environment. So we consider the quasi-static load, which can be worked when we launch the system, and also vibration and random vibration loads, a harmonic and random vibration load. So we did the quasi-static analysis and harmonic and random vibration analysis. So these red circles shows that the boundary condition, which is the fixed position of this whole system. So for quasi-static analysis, we put the mass acceleration curve for the quasi-static load. This indicates that actually calculates that the maximum acceleration by some specific mass of the payload. So we can calculate the bound of acceleration with this equation. So for our case, so our mass of the LFTMS is around 10 kilograms. So that corresponding to around 4 EG. So we put this 4 EG for all three axes. And this figure shows that the stress plot. So in each axis, we pick the maximum stress point, and we compare this maximum stress with the yield stress of the material, which is 2.71 megapascal. And then we calculate the margin of safety. So if the margin of safety is positive, we can say this system is quite safe for this environment. And if this margin of safety is negative, it indicates that the design failure. So if you see this part, we have all positive margin of safety for all three axes. So this is quite okay for quasi-static world. And also we need to do some model analysis to calculate the natural frequency of the system. So this is the payload system for satellite, and this will be mounted on the launch system. So we need to avoid the natural frequency of the payload and the launch system to avoid this resonance phenomenon. So normally the launch system require the natural frequency for the payload system higher than 100 Hertz, and our natural frequency is around 121, so which is quite okay for the general requirement. And also we picked 5 nodes for each mode of frequency mode. In this node, we calculated harmonic and random vibration analysis, vibration loads. So this is the input value for the harmonic and random vibration analysis. So this input values come from the Soyuz launch system. So this is one of the examples. So this shows that the response plot. So for the harmonic analysis and the random analysis. So if you can see this black line here, these black lines are actually the input value that I just showed you last slide. And this color, like red, blue, and magenta colors are response, which is the result of the simulation. So you can see there is some peaks in specific frequency, x-axis is frequency, so there is peaks. These peaks, this frequency actually match to the natural frequency of the system that I analyzed in the model analysis. So I got the maximum stress value in that frequency for both simulation. So for both analysis, for all resonance frequencies, I pick the maximum stress and compare with the yield stress. And then I calculate the margin of safety, which is almost the same process. So you can see here, there are all positive margin of safety. So I can say that this is quite okay for the harmonic and random vibration analysis, also for quasi-static analysis. And very first part of my presentation, I showed you the mirror design. There is shims and air bracket between the optomechanical structure and the mirrors. So by changing this thickness, we can actually adjust the mirror position. So for instance, if we have some errors from the alignment process or the fabrication process, like tilt or decenter of the mirrors, or dispace, which is the intermirror distance of the mirrors, then our optical performance will like degrade by this error. But by adjusting this position, we can actually maximize the optical performance again. So to do that, we measured all coordinate of mirrors, fabricated mirrors, and optomechanical structures. And our student, Ho Jae-an, calculate this shim adjustment and air bracket adjustment values by using the CNN measurement result. And for instance, if you see the M2, this brown color shows that the shim adjustment values around 4.5, 4.8 is around that. This is quite large because there were some problem with the fabrication process of the M2. So we adjust these values to make it repositioning of the mirrors. And in this process, we only compensate the tilt and decenter, not the dispace. Because from the sensitivity analysis, we found that the tilt and decenter actually degrades the optical performance significantly than the dispace. So we only compensate these two values. And the left one is the simulated one with the misaligned errors. So you can see a large spot size. Then if we optimize the system, we do have like nominal design, but by design. So, and then we also measure the optical performance, not only center, but also for all field of view. So if you can see, there is no dramatic optical performance degradation by linear astigmatism for all field of view. So this is the optical performance result. So to summarize, so we designed the confocal phase system, which removed the linear astigmatism, and we fabricated mirrors with aluminum, and optomechanical structures consider also straight line suppression, and these structures are safe for vibration environment for Soojong 2 launch system. And there is a mirror alignment mechanism for the optomechanical design, so we can optimize their position to maximize the optical performance. So this is my presentation. Thank you.
끝까지 함께 해주신 회원분들께 감사드립니다. 네, 마지막 발표자이신데 아직 시간 조금 있으니까 질문과 코멘트 그리고 디스커션을 계속 이어가 주시면 고맙겠습니다. 예.
Thank you for giving your talk in English. My question is, what wavelength of light does this system work over?
This is payload, sorry, the prototype for now. So we can use this. So originally we targeted on this system for the IR observation with the wide field of view observation. So we can observe like Pastel alpha line for galaxy in galaxy plane, and also Soojong line in middle infrared range, this is the satellite payload. So, and also the CIB observation for infrared wavelength.
Do you think it would be possible to shift towards bluer wavelengths like the infrared?
We think so. Yeah. So, and this is a mirror. Basically, the optical design is basically from the mirror system, not the lens. So this is not wavelength dependent. So it's quite okay.
다른 질문, 코멘트 없으시면 시간을 딱 맞게 6시 30분에 마쳤네요. 그러면 이것으로서 첫째 날 전문 우주 관측 기술 세션을 마치도록 하겠습니다.